Okay, I think this is a fairly quick and easy one if I am not mistaken. So we've got a curve on a racetrack which we can at least model as being a circle. It has a radius of 20 meters. And there is a car on the curve, which I can model as a box. And it's traveling with a radial velocity. In other words, it's rotating at 0.7 pi radians per second. Now, there are 2 pi radians in a full circle. So this is traveling at 0.7 pi radians per second. So it's going to take 2 divided by 0.7, whatever that is. I can't do it in my head, but it's a little over 2, approaching 3 seconds to do one complete circle, if it were a complete circle. So, and 0.7 pi, if you calculate it out, is 2.2 radians per second. So it's circulating around. We know that the centripetal acceleration, A, is equal to v squared over r if we know the linear velocity. Now, in this case, we don't know the linear velocity. We don't know this. We could figure it out. That's one way to approach this problem. And, this is something that I'm going to talk about a fair bit, is that there are multiple ways of approaching a problem. But in this case, we also have another formula in terms of radial velocity, which we might as well use, since we have a radial velocity, which is A equals r omega, where omega is the velocity in radians per second rather than in meters per second. So instead of A equals v squared over r, A equals r omega is the actual centripetal acceleration. So this car, because it's going in a circle, is accelerating towards the center in order to keep going in a circle at that rate. And we can just combine that one with our good old Newton's second law, F equals ma. So replacing A with r omega, F equals mr omega. So that's actually incredibly straightforward. I'll give myself a little bit more room to get a run at it. F equals mr omega equals the mass, which we're told is 1270 kilograms, and I probably should have summarized that at the top. 1270 kilograms, I'm putting the units in here, times the radius, which is 20 meters, times the rotational velocity, which is 0.7 pi radians per second. And overall, that's going to give us a centripetal force of, don't know why I put an F there, cross that out, 55,880 Newton. Newton, I guess, is the correct thing. So this is the centripetal force acting on the car to keep it going around the corner. It would have to be provided by the tires, so that's quite a large force in order to not slide out off the corner. That's the force that the tires have to provide. And just thinking about it, if we just actually do A equals r omega, that centripetal acceleration is equal to 20 times 0.7 pi, or 2.2 actually is probably simpler. 20 times 2.2, 44 meters per second squared is the centripetal acceleration, which is equivalent to roughly 4.5 g. Now, jet pilots who aren't wearing pressure suits for high G can pass out at about 5 or 6 G. So 4.5 G is pretty extreme. It's the driver is experiencing a sideways force 4.5 times as much as the downward force due to gravity. So that's pretty full on. So this is probably some kind of racing car. It's not your family sedan. It would have slid off the corner long ago at these kind of speeds. So that hopefully gives you a sense of what that centripetal force looks like.